Okay, good afternoon, everyone. My name is Ziliang Zhao. I'm a PhD student from the University of Tennessee. So I submitted this position paper entitled Developing a Space-Time GIS Data Model for CyberGIS with my advisor, Dr. Ziliang Zhao. We are not part of this project, so I want to thank the project committee for this great opportunity. So in this presentation, I will briefly talk about our part of our research in space-time GIS and how we can contribute to CyberGIS. So as we know, we are in the big data era. The scientific paradigm has shifted from experiment, theory, computational simulation to the so-called the fourth paradigm, data-intensive scientific discovery. However, as Jim Gray pointed out several years ago on eScience, we still lack good tools for both data curation and data analysis. And this is also true in GIS. Nowadays, we have overloaded data which change in space over time. For example, GPS tracking data, VGI, sensor network data. Therefore, the design of space-time GIS data model becomes extremely important because it's a way how space and time are represented with GIS. And it also decides what kind of questions we are able to answer based on the data we have. And space-time GIS data model can contribute to CyberGIS because it provides a solution to better represent the dynamics of different kinds of phenomena. In addition, innovative tools can be developed to facilitate problem solving and knowledge discovery. So we know that in GIS we can handle the spatial domain pretty well, but we have been struggling for a long time to incorporate the temporal domain. Here we list some representative space-time GIS data models in the past 2 decades, and we can say that the efforts to come up with an efficient and robust space-time GIS data model have never stopped. And however, most space-time GIS data models are still space-dominant, and time is considered as a property of spatial objects. So this space-dominant perspective limits the dynamics we are able to represent because time can be so complex. Time exists in various forms. It can be time point, time interval, time cycle, time branch, and so forth. And this figure shows an example which can be my activities during the day. I can say hello to my friend, which occurs at a time point. I can talk to people, which can be a time interval. And I can use time branch to represent the uncertain future or uncertain past or undetermined future. And I can also have recurring behaviors, for example, going to a conference session and then take a break. So this example demonstrates how complex time could be, and we have abstracted different forms of time and created corresponding components in GIS to be able to represent different types of time. And one challenge is that each entity in the real world is associated with different types of dynamic information, for example, dynamic geometries, attribute values, and activities. And each of these properties can change in a different way. So how to integrate them under a unified framework? To address this problem, we borrow the idea of linear referencing, which is widely used in transportation to manage transportation data sets, such as road quality, speed limits, and so forth. And we can retrieve and analyze any roadway events by specifying the attribute name and the milepost values. So this is called dynamic segmentation. And with temporal linear referencing, we can consider the change sequence of a property, such as one's trajectory, as a road, and the status of that property as roadway events, and time as milepost values. So we can use multiple parallel timelines to represent how properties, to represent the change sequence of different properties. And with temporal dynamic segmentation, we are able to locate any geometry, attribute values, or activities at any time. And we take an object-oriented approach to to implement this idea. So with our design, each entity is an object, for example, a person, and this object can carry one or multiple parallel timelines which represent how properties of this object change over time. Such property can be geometry type, attribute type, or activity type. So we can handle different types of dynamic information pretty well. And each timeline can consist of different types of time units, for example, time point, time interval, time cycle, time branch, and so forth. So the change sequence can be very flexible because time is no longer subordinate to space. So based on temporal linear referencing and temporal dynamic segmentation, we can develop new spatial temporal analysis functions beyond what traditional GIS can offer. Due to the limited time, I only show two simplified examples here. So the upper figure shows how the ST-intersect tool can help find out potential interaction possibilities between two persons, given the dynamic potential path area of each person, and the Z domain represent time. And the lower two figures shows how the ST-dissolve tool can find out the place and duration that multiple people visited at different times. So these tools can potentially be integrated with CyberGIS framework, so different people can use them for different types of analysis. And we take a similar time-oriented approach to create a space-time GIS data model for temporal remote sensing data set. So with our design, each pixel is an object which includes information from different remote sensing products at a specific location at different times. And each timeline of this ST object stores the change sequence from one particular remote sensing product. And also we can use time point, time interval, time cycle to represent how values change over time. So this design offers two major advantages. First, it's much easier to track locational variation from a temporal perspective. And second, it allows various spatial temporal analysis functions to be defined on each object class. And we use this approach to evaluate a spring freeze event around Knoxville, Tennessee in 2007. We collect three remote sensing data sets, NDVI, LAI, and GPP, and we collect the data from the beginning of 2006 to the end of 2008. And we use K-mean to classify the study area into 15 clusters in terms of the temporal variation pattern at each location. And we can find that certain cluster exhibits abnormal temporal pattern in 2007 compared with the temporal pattern in 2006 and 2008. For example, this figure shows the temporal variation pattern of NDVI of one cluster from 2006 to 2008. As you can see, compared with the change pattern in 2006 and 2008, the change pattern in 2007 suggests an earlier and warmer spring, followed by massive vegetation decimation, which is the consequence of the spring freeze event. And then the vegetation recovered again. So we consider to integrate with the high-performance computing to handle big data sets. Since we rely on E3 product for spatial data access, storage, and analysis, our platform is kind of special. That is, we adopted a Windows-based environment considering the compatibility with the ArcGIS. And we use the Microsoft MPI, which is MS MPI, to handle distributed geoprocessing. And we packed the spatial temporal analysis functions that we developed as modules so they can be called directly at runtime. Okay, I think I ran out of time. So this is some conclusion. Thank you very much.